So today we're going to be deriving Betz's law using momentum and energy balances. We're looking at an optimal turbine where all of the energy that is transferred to the turbine is fully generated or is used to generate power. So 100% efficient. And it'll have some outlet, A2, V2, and some inlet, with the outlet having a larger cross-sectional area than the inlet. And the inlet having some velocity of fluid higher than the outlet. So V1 is greater than V2. And we're looking to derive the optimal ratio between V1 and V2 in this case. The turbine is going to have some cross-sectional area S, some velocity V. I keep pressing the button on this pen so it's not writing. And we're interested in the mass flow rates, so we'll multiply everything by the density. And like I said, we're going to be using momentum and energy balances, so we'll start off with momentum balance. We have the change of momentum of the system with respect to time is going to be equal to 0 because we're at a steady state. And that's going to be equal to the change in velocity. Let me rewrite this. V1 times mass flow rate 1 minus V2 times mass flow rate 2 plus the force exerted on the system. And we can rewrite this because we know that the mass flow rate 1 is the same as mass flow rate 2. No mass is lost as we flow through the system. So it's going to be the same as it is at the turbine, which is just equal to rho SV. So we can go ahead and plug in rho SV here, and we'll move the F to the other side. And we have negative F is equal to V1 minus V2 rho SV. We know that power is equal to the force exerted times the velocity. So we know that F is equal to P over V. So we'll plug that in and then multiply across by V. So we're left with V1 minus V2. Well, power is equal to V1 minus V2 times rho SV squared. And then we can do the same thing with the kinetic energy balance. And actually, let me put a box around this so we can find it easy, because we're going to be using that again later. But we know that our power is equal to the change in kinetic energy over the mass times the mass flow rate. Let me put that dot actually above the M there. So we have power is equal to 1/2 mass times V1 minus V2 squared times the mass flow rate all over the mass. So these two masses will cancel out, and we can plug in rho SV for the mass flow rate. We have power is equal to V1 minus V2 both squared rho SV over 2. So from here, all we have to do is set these two equations equal to each other. Well, that's not all we have to do, but the next step is setting these two equations equal to each other. And let me see if I can just move this down. There we go. Look at that. So we'll start off by dividing across by rho SV. So we're going to have V1 minus V2 both squared over 2 is going to be equal to V1 minus V2 times V. We'll divide across by this V1 minus V2, and we'll also factor this term. So we're going to have V1 minus V2 times v1 plus v2 over 2 times v1 minus v2 equals v. Can cancel these terms out. We're just left with v1 plus v2 over 2 is equal to our velocity. So we can go ahead and plug this back into one of the equations. So from here, all we have to do is plug this into our energy balance equation. So we're going to have power is equal to v1 minus v2, both squared, times rho s all over 4, because this 2 and the 2 in the energy balance equation, times v1 plus v2. And then we're actually going to multiply these two terms through. Make sure I'm recording. So we have P equals v1 cubed minus v2 cubed plus v1 squared v2 minus v2 squared v1 times rho s all over 4. And actually what we're going to do here is we're going to take out a v cubed from each of these terms. And then we'll also move the rho s4 out in front. So we're going to have p equals rho s v cubed, sorry, v1 cubed I should say, over 4 times 1. And I'm going to rearrange a bit as I do this. Times 1 plus v2 over v1 minus v2 squared over v1 squared. Nope. v1 squared minus v2 cubed over v1 cubed. And then what we're trying to find is the optimal ratio of the outlet to the inlet flow. I think I said inlet to outlet before, but the way we're going to look at it is outlet over inlet. So we're going to have R is equal to V2 over V1. So we're going to substitute that in for each of these terms here. So we're going to have P, and well, no, I'll keep writing it. We have P equals rho S V1 cubed over 4 times 1 plus R minus R squared minus R cubed. And then we're going to take the derivative of this. The derivative of the power with respect to time is 0 because we're at steady state. The amount of power we're generating is not changing. So we have 0 equals rho S V cubed over 4 times 1 plus, so this becomes a 0, this becomes a 1, minus, you need a minus here, not a plus, minus 2R minus 3R squared. And then since this term here is going to be positive no matter what, you can't have a negative velocity. Well, I guess you could if it was flowing backwards. But in this case, it's going to always be positive, or non-zero, I should say. We can go ahead and ignore that and just take the root of 0 equals 1 minus 2R minus 3R squared. So we'll go ahead and factor that. We have 0 equals, let's see, we have, I think, 1 minus 3R, and then 1 plus R. Yep. So we have R equals negative 1, which of course doesn't work. And we have R equals 1/3, which is our root. So Betz's law states that the maximum, or the optimal ratio of the outlet to the inlet velocities is 1/3.